Where? Okay. This is right. Share हो रहा है? How to remove this? It remains there. Okay, what she's saying. How to remove this back? Just click on. Okay. Yeah. Bit of technical glitch. Start. Yeah, so basically, just to give a rough overview, like what we saw last time was like we had this forward graph capture and like we were dealing with the dynamo thing and we ended at the dynamo part, which is the front end. So today I have plans to just go into the back end, like as in AOTAutograd and inductor. Okay. So basically just to give a rough overview of what happens in here. So like this thing is okay. Now see like this is the graph capture, like as in if you see the entire picture of how this PyTorch 2.0 framework works, like the graph capture is a like forward graph capture and that is done by Dynamo. Okay. Now after this like, keeping this line as a separate thing, as assume ki like this part from this after this graph capture, this is a portion of the backend. So backend calls this AOTAutograd, which what it does is takes the forward graph and tries to trace the backward graph as well using this forward graph itself, and like and does the automatic differentiation, and that is how it does the gets the backward graph. And like AOTAutograd, like this is a part which is done by AOTAutograd, and AOTAutograd also like converts, like lowers the IR down to 18 IR. Okay. So like after that there is optimizations based on the 18 IR. Okay. And like stuffs like operator fusion, memory planning and all, like the buffer, like the chunk of memory which it can hold, take together in one go, something like that. Then memory aligning and all. Okay. And after that we have this code generation, and based on whether you are using CPU backend or GPU backend, you have OpenMP and like or Triton for CUDA. Now let us go into it. So for today's like this part, I shall be taking a very naive function to just show how the forward pass and backward pass works. So this is a constant function. Okay, sine square x plus cos square x, its value evaluates to 1. Okay, now if you differentiate it, it shall be a 0. Okay, so now this is the like this is the forward function. Now like we have basically seen this in the last Torch Dynamo Reset does like flushes everything, flushes cache, guards everything, and does like us like from everything from scratch. So I was trying making plans to use this thing in a lighter manner for that guard thing I told, but yeah, I shall discuss it later. But yeah, so basically, why I wrote that reset, because it is like a tool, it is an entire single notebook, right? So everything, like if I do not do the reset, like previous small examples shall interfere with the new. So like everything clearing it out, as in like this is a fresh example altogether. So, yeah. So basically, like I am doing the same thing here, like what I showed previously. I'm just taking the dynamo and just printing it out. What is the graph for the timing? I am not yet using the like AOTAutograd and all. So probably I have given you guys a yes, it does symbolic execution on this function. Like as in, I won't be saying control flow. Like control flow happens at a different level altogether. Like they like yeah, it is tracing it, but control flow in the sense like if there is that control flow kind of thing, like if I say like FX graph won't be no, right? It is not there. There is no control flow. This is just like as in this is the function which is there sine square x plus cos square x. So there is as in this is there is no control flow as in x is there. It is doing sine x cos s like it is showing like these operations can be done in can be done in parallel. Like there is no dependency as such. This is like symbolic execution and data flow mostly. And like they say ki like it has symbolic trace, like they do not pass in like for this thing they name it as symbolic trace because they do not pass in actual data. Yeah, so that is yeah because they don't have the data. So parallelly they do like pow like they do sine square x cos square. Yes, like these are parallel nodes, like this operations can happen in parallel. Like I like in their documentation they have maintained few like to get an exhaustive list of that I need to look into the source code that FX graph. No, I don't think so. Like in their paper, the original FX graph paper dates back long back. After that, like whatever I have seen, I have given two examples. Like one was that ki, like if there is a function like sqrt or length, you cannot just do it. You need to just do wrap and all. And another one naive example is that if there is a control flow, if something else something, so there is a it cannot trace. Like you need to do FX graph break something. So these are the two like major examples which they give to motivate ki like FS graph is powerful but not that powerful to deal with everything. But yeah, like the documentation, like the problem with this thing is like it is evolving still now. Like things change in a day-to-day basis. So the documentation which they have in their paper and all, like it is very outdated. Like the paper is very old. Anyways. So like this is just to show the annotation ki, like this is what is happening and if you look into like this is the forward this is nothing like this. It's the after the annotation it is doing this thing. Now if you look into it ki, like if you try to do like the differentiation of it like this is like this is the value which is there and this will cancel out and actually become zero altogether. Nothing fancy in here. So next what I am doing is uh, the dummy compiler which I wrote, which was just doing the Dynamo part and just giving out the torch IR, right? So I just did one level up. Ki, like don't just stop at Dynamo. Uh, so what it does here is in this like inspect backend is something some custom compiler which I wrote. As in there is this forward function and there is this backward function. Like they like forward compiler and backward compiler and internally it is calling AOTAutograd. Okay, and we are passing the forward function and backward function like forward compiler and backward compiler to this AOTAutograd. Okay, so like these are just hooks. You can just do whatever implementation you can have in inside. So basically, what is happening in this dummy forward compiler and backward compiler is that I'm just getting in whatever is passed and I'm just printing it out as a graph thing. Okay, very like very naive. So basically, this is the two graphs, like the forward graph and the backward graph. And if you want to like after the annotations, they like what they say is they try to do so many things. Yes, yes, like yeah, yeah, yeah. I am zooming in, but just to give or something. Yeah. So, like this is the forward graph. Like the left side is the forward graph. Like we have seen ki like sine x, sine x, cos x, sine square x, cos square x. Like and then adds it and returns it. No, 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 no. Like on Which one? Left side? Yeah, yeah, like as in metadata, this is how, yeah, as in like what opcode is passed. Like this is a function call for sin x, as in like and this is the thing below it here is the function call for power. Okay, this is like this it is IR. Okay, so for each operation there is some kind of a node which is represented. Yes, yes, like something similar. And now if it is like this is the forward graph, but if you want to understand ki, like what is the backward graph, so basically like what happens is use like it does something using the forward graph itself, it tries to generate the backward graph. Okay, so like as in this, it takes in these nodes like this sign, this percentage sign x, this percentage, as in like whatever examples till now I have seen, it is able to do that. Like there might be some cases. Which one? Like if there is training, right? For like it is not always always useful if you are just doing inferencing, but if you are doing training stuffs and all, like this is when this backward graph shall come. Like this is backward automatically. Nice. So yeah. So what it tries to do is like the same thing, like cos x sin x, raises it to the power of one. This is like, yeah, and just calculates this thing, like it shall cut off. Like the differentiation it does automatically. What one thing which is to be noted here is previously the operations which we were seeing here, right? Just as in here, if you can see, it was like as in torch dot sine, torch dot cos, right? This is the torch IR. Okay. Now, if you see the AOT autograd thing, here they have reduced it to like torch.ops.atten power 18 sign. So like this is like they have reduced it to 18 IR. Okay. Now, like if you just want to have a look of what are the IRs which are there in this PyTorch altogether. Like this is not something specific to like PyTorch 2.0. Like this is it dates back from PyTorch 1.0 itself. So like first of all, we have the PyTorch API, as in like some sign, cos, something like that. Uh, uh, Torch, I shall be coming to that picture. It is something here. Torch IR is like Torch IR forms this portion. Like PyTorch API, then you get Torch IR, and then it is lower to 18 IR, and then ultimately Triton IR or OpenMP something. Like the Torch IR forms this portion. They name it as FX graph IR or Torch IR. So basically, like 18 IR is something like they lower every PyTorch API to 18 IR. So there is something known as core 18 IR and prims IR. Like these are even lower than like and has like a subset of operations, and they are more primitive in some sense. Like core 18 IR is designed to work on certain AI accelerators, and prim IR for some ASICs and all. Like I'm not going into these two things. Like 18 IR is what PyTorch 2.0 works with. Okay. So now, yeah, we have a lot of like now let's throw away our like dummy compiler which we were using. This is the dummy compiler, right? Which we were doing. Like now let's dive into the original inductor. Like if you are using their own their backend, like inductor backend, so Triton is a part of it, and they shall be using Triton to do GPU stuff, but you can as such write your own backend, as in like the way I was writing, right? Mm, as in yes, like whatever I have seen is like the operator fusions, etc., whichever it can do. So apart from there, kernels which are named as Triton underscore some weird number. Those are the kernels which are generated by operator fusion and all. But apart from that, there are some generic kernels, like as in like which you can understand, ki, like some kernels which are not Triton kernels. Some operations, like as in whatever Triton cannot handle, they shall be launching like basic kernels altogether, yes, something like that. So like they are generic kernels altogether, which are provided by them. Like they might be. Mhm.
Plan to completely do away with their dependence on plus today and ultimately Triton will encompass everything. Is that the plan? What they're going to?
I don't think so, because this the libraries which are there in Kublas, those things and all, like they are highly optimized in some sense.
They
So
don't try to.
like I don't think it would be beneficial in just poking around that thing. Like they are like
NVIDIA, yeah, from that perspective.
like their main like as in Triton was a kind of a programming language using which you can write CUDA kernels in an abstract manner. Like you do not have to go down to the level of CUDA thing, but like even like and it works with torch. Okay. So and if you are trying to use some operations and all, like internally it shall do the mapping ki, like whether I shall be writing my own kernel or internally call some kernel altogether. I don't like what I feel is like this Triton abstraction works on user level code altogether. Now, like we like the user doesn't have control as such ki, like whether I shall be using some Kublas library altogether. Like it shall be just using some torch function internally, that wrap function. Uh-huh. Mm-hmm.
Is essentially it goes back to blast, 2D and all those close source one versus things that are actually gathered by Triton.
Like what I have seen, like I cannot say that the exact percentage, but that kernels, the generic kernels which are which gets called, they are very less in amount, very less. Like just to say like 80-20 something. Like they are very less. Functionality that Titan can give, for example, operator fusion itself, is because the operators are very simple. Like, those things are not necessarily too dependent on. For example, if we do side X, I don't think they need to really call who does the matching or something. No. But for mathematics, which is gem, like gem sort of thing, I don't think they can beat. So far, they cannot do that. That's what polymer is trying to do. But gem, they cannot do anything about automatic generation for. So, like, what decision they take, that is built into the core of
So you're
Triton.
saying that the same,
Yeah.
this for the chain and so on, this fall back to.
I think there has to be some heuristic decision at some point in the whole code.
Should I decide if money hand or not?
Yes. Yes, as in. Because I don't see any other.
But those heuristics can change over time. That's what I'm saying. Like, whether your plan is to go ultimately clear it off.
Yeah, but that is what I think is something that is not very aware of. Yes. How that happens. And as in like whatever I have seen, ki, like from my experimentation, Ajay was also there. Ki, like if you are writing a Triton function, they name it as Triton kernel, but let us name it as Triton function. So internally it shall be like creating certain 2 to 3 kernels, and they shall be mapping that functions operation to those kernels. Now, like as in you are writing from your side of Triton function altogether, some like abstract operations which you are using, and internally it maps to like what kernels it shall be mapping to. Like there shall be 3 kernels like Triton.
That could actually change.
Yeah.
They can do the mail address, they will probably fall back to using
Kublas. Yes. I think they use Triton. Yeah.
Yeah, I mean, I think it's mostly heuristic. Because this operator fusion and stuff is in itself a lot of heuristic based decisions. There are a lot of people.
Sometimes like in fusion, in green of field separation might not give you much benefit. Depends on what are you using.
Exactly. That's the heuristic part that most I think a lot of papers also.
And all the fusion will have some of that. Like there isn't.
Yeah, I mean, I think what most papers will try to do is increase the let's say, coverage of what our operators can use.
What?
Increase the coverage of
Yes.
They didn't get this one. What? Like.
and most of these, I'm talking about not right, but recent papers that generally talk about fusion, operator fusion. I don't know, I've not seen much recently, but since I think in 2021, there are a lot of papers that will just talk about how we can fuse more operators.
Yeah, basically what will happen is that there will be more and more models which will have these combinations that currently is not covered, and they say, oh, I can fuse it.
So like this problem of what operators it can fuse and all, this entire PyTorch 2.0 backend and all tries to get away with this in some form. Like they take the higher level operations and they lower it to primitive operations. Okay, so a single complicated operation might be lowered down to say like 10 primitive operations, and the fusing which they can do, right, they are on this primitive operation. So they're as in like the concept of like whether I can fuse a new complicated operation or not kind of goes away. They have to deal with that higher level like whether I can take this new operator and lower it down to more primitive stuffs and all.
No, the memory and everything, right? So some of that also is captured in the photograph.
But they cannot get rid of memory writes that are happening on the,
If you are doing global memory access, you can continue that to the others. That's
fusion cannot.
Yeah, what is I didn't get this.
Okay. As we
That's what they should target next. You should be able to figure this out. You actually just things out, but you can like how do you change programming? No, like
at Kudala it is difficult, but it is
that was because there was something to that. No, even so basically then you are actually doing in some runtime fusion or something, whatever you call. Runtime automatic fusion or something.
we need some sort of data flow analysis at runtime and then figure it out. It gets difficult. So I think that's what they rely on these abstractions at higher.
Like I am not getting this context. Like what are you talking about? Like doing some kind of optimize like fusion in CUDA graph. Mm-hmm. Mm-hmm.
When we are talking about fusion,
Mm-hmm.
can CUDA it's the executed values giving it the benefit of the capture velocity.
Mm-hmm. Right now it is. Mm-hmm.
Fusion means more.
Yes. That also you are actually writing because you have the addresses. So with some hardware support you can
We should be.
Huh?
We should be.
But you should be able to do it. Because you know the addresses and so on by the time. Up till the physical address you know.
Okay.
Simulator. But if you are NVIDIA, you can do that.
I don't know. I don't know whether they prefer to put more silicon and adding another SM, having this sort of complexity.
Just write another fuse.
Yeah, I don't know.
So let's wait for people to write up with this fuse version. Then MD should do it. There will be actually a differentiation. MD doesn't have programs, right? Big graph.
The big graph. Something similar they have.
Yes, now we can. This we can see.
Like, and this,
This MI300A is not a joke. I know AX. MI300X is not a joke. That guy packs for. That's just the
Oh, 300. Oh, it's a new one.
250 is the one. They gave us the older one. And that's good. 300 is good. So that's the problem. Yeah, hardware is good. Actually, if you look at the flops, in fact, better than the NVIDIA, of course, the price time, everything is far better. That's the lowest. Memory amount is better. But thing is, the software stacks up. And what they say, they also know they can't catch up. So everything open source of, and then this is debating. Can happen, it has happened, right? So this kind of thing can actually catch up. Once it starts standing up, Microsoft should be this. As a direct.
Microsoft has a big interest. I don't know who are working. There were some folks who were working on it, but at a bigger scale,
Because it can directly impact the cost.
they're not cheaper.
I was talking to the desert and some guy invested in. It's like right now. Right now, he's not interested. He's like, because no one is too much interested in
So
it.
that's the thing, basically, if the big market is, if this startup actually says that I'll give you performance equivalence, most of the applications, you don't worry about, you just worry about your convergence, how long it is, taking and all these things. These are the metric I'll give. You don't have to know about what I'm doing on what, I'll give you lower cost. A startup can do that, huh? That will make millions.
yeah. So like what when
I don't know why Microsoft don't have it.
There are many small scale efforts. They were at least now I'm not aware of it. But I don't know that. And this
So you see, like, it makes a lot of economic sense.
makes
yeah. So basically now I have just chopped off the dummy compiler which I was using, and I am using the full-fledged uh, compile. Okay, backend is inductor. Like the default is inductor, but still I am just being explicit here. And like these are a few options which I have added just to dump the. I have to check, but there are like as in like, there are alternatives like as in
So that is
like
also very much.
the NV Fuser, AI template, and other stuffs are there.
So that NVIDIA user thing is the NVIDIA.
Yes, NVIDIA Fuser and all.
So how does the performance, if you change the backend from say inductor to NVIDIA user, does the performance changes big time?
I haven't tried out these guys, and I don't think they are as powerful as inductor. Like they are less powerful in some sense. Like they can deal with some special cases of stuffs. Like this stack which they have mentioned, right? This Dynamo, AutoGrad, and inductor. This is the most commonly used thing because this is the default. I do not have it. I have. I need to check it. Like I didn't look into that, but I have just heard the names, as in like there are mentions, but I didn't dig into it. Yeah. Yeah. So basically I took the same program and passed like same function and passed through this inductor backend. So let's see like what happens now. So as you can see here, this is the inductor IR. Okay. Now if you can see the number of nodes have drastically reduced. So primals is as in like the X. Okay. And the thing which we were having, right? Sin x, cos x raised to the power of 2, and then addition and all, then getting the output. Everything reduced to a single node, and that's name is like fused add cos power sine. Okay. And for the backward graph also, like there are like this is the x, this is some constant t which they generate using like as in some constant, and you have this fused at cos like the entire thing which was happening, right? They fused it to a single thing here, Now, if you just to have a look at it in like pictorially, like this thing which we like entire whole thing gunk reduced to a single node in here. And the torch inductor actually internally makes use of some IR which is named as like defined by none loop level IR. Like why the name is like let me explain it. So the IR some like for each buffer which it is computing, right? Like for each buffer which it is computing, like they spit out a IR something like this. So this is some the point wise means each element of the buffer shall be using this pointwise operation to generate what the value should be for that buffer's cell. Okay, so basically it happens in in the following manner. uh, it takes in an index, and based on that it like from that index it loads something, creates a sign out of it, squares it, and then again loads it, cos it, creates a cos out of it, multiplies it, and just does like sine square x plus cos square x, and then returns it as is. Now, like here, like ranges means like the buffer's length is 1,000, and these are some other metadata and all like node origin add, and this is not going into it. But if you can see here why it is named as defined by run loop level IR, like defined by run, like this is some kind of an IR which they named as such. Like why it is named as defined by run, because this ops which are mentioned here, right? These are some objects like or function pointers which they can overload during runtime. So basically what might happen is when you are doing some kind of an operator fusion thing, this op shall point to some class which does the operator fusion. Okay, so same IR shall do operator fusion for you, and then this ops whatever it is, like you can just overload it or change the function pointer to it to some code gen class. So basically the same, then the same IR would generate the code for you, do the code gen for you. Okay, so now if you look into this pointwise operation, like you just have had a rough idea like what it is doing. So this is how the Triton kernel internally looks like. Okay. So there are some import stuff like this is actually, so what they do is Triton UI fused add cos sign, this is the handle to automatically.
No, that is fine.
Huh.
And this is not cheating, right? Or
As in
when it is actually
like what happens is JIT
spit out.
JIT happens here as well. Like as in what happens is they during the like the first time when you run a function through it, there is Dynamo AOTAutograd, and then there is this Triton code gen. So this Triton code gen is something like this is a file which gets generated in your temp directory. Okay, and there are pointers to make use of this directory. And when like you see here async compile Triton, okay, and this entire code is written as a string. Okay, and internally this which is annotated by @triton.jit. So this shall be just in time compiled. So there
Different ops that you pass.
no, like because like this @triton.jit is always there in each of the Triton kernels which it spits out. I did not get your question then.
What is really what is happening? What is really cheating?
As in like this part, like the just in time compile, like, as in when you try to run something, it shall trigger the compilation of this Triton code to PTX and all, and keep the handles of that PTX code with itself. The next time when you shall be calling this Triton kernel, it internally it shall call those objects.
It is good towards to PDX.
Yes, from Triton to there is PTX. Intermediate there is no CUDA stuffs.
That's fine.
Yes. So this is the this is the high level overview. Like I do not know into the very details of how this compilation stuff happens, but yeah, like this is what the idea which I have. As in there are two level of stuffs like asynchronous compile, as in this whatever there is in this string, it shall compile it and create an object code out of it. And when you try to run that, like there are two level of compilation happening here. It is compiling it and generating some kind of an object code. Now, when you try to use this Triton function, like it shall be hitting that compiled object code. And then when you use this Triton kernel, there shall be a just-in-time compilation which shall do your PTX thing and all. And furthermore, they shall be just using that PTX alt. That is what I feel. And yeah, now if you try to look at it, how it maps, like the Triton kernel, right? Like as in how you write a kernel, you write operations for each of the index and all. So similarly, like some similar stuffs are happening in here. You use okay, like tl.load, math.signs, like squaring it, then cost, squaring it, and then adding it. It is similar to this defined by run loop level IR. So they just used this, like overloaded something and spitted out this code. And just to have a look at it, like this is the forward graphs node, and this boils down to something like this. Looks, but it is not.
By the way, if you can try to now make it quicker.
Yeah, it is. This is the last thing. Uh, Yeah, so like this is the forward graph and this is the node, and like this is the Triton code which gets generated. Yes, I can show you if possible. How this is how the Triton code actually, like this is in your temp directory. These are how the codes look like, as in some various stuffs are there. This is the sync Triton compile, and here is the call function which does some empty strided CUDA stuff. So like as in these are the buffer aligning and all, and then they do some more operations on the buffer and then call this compiled thing. Okay, this is, and this is the call function. And when you are using that reduced overhead thing, they try to wrap this call function with CUDA graph. Like this call function is wrapping your Triton call and all.
True.
Okay. And this is doing the buffer management and all. Now when they like they when you try to do reduce overhead thing, so basically internally it shall be using CUDA graphs. So they have to wrap some function with the CUDA graph. It is this function which they wrap with CUDA graph. This call.
So if you try to create a use the photograph for only this is the node or this is the graph.
Like
That
like this, it shall try to do graph capture on this call.
basically
And
this is a single graph.
no, like as in what graph are you talking about? CUDA graph? No. Like as in yes, like this here, yeah. So this is the CUDA graph, and internally based on what kernels are on, it shall be having different nodes. Yeah, yeah. Sorry, you do capture on this thing. Yes. This is what is I was yes, like everything
Each for is one
one FX graph. So that is what I was
and
saying.
one photograph.
Yes.
So the okay. So
But it can have any kernels.
Yeah, of course, you can have that. Otherwise, what's the point?
So basically, just to this forward graph is an FX graph.
True.
So like this is the AOTAutograd thing. Now, if you look into the torch inductor thing, this is an FX graph
In a fused format.
in a fused format. This thing, this wiggly line thing, this is the this is the entire thing is an FX graph.
The entire thing.
Like this whatever is shown like forward graph, this is the FX graph. This is this internal node is the Triton, that Triton function. Internally, it is like the call function is actually calling your this call function. Okay, it is overloaded there. Yes. Why?
Each node is not called.
Like
Why do you think that?
Oh, it's a top one is just a placeholder. Office placeholder.
like I am not getting your
No,
doubt.
no. It's on the calls. Basically, the extra on the calls should be in operators. When you call, you have a corresponding call, and that is what you will actually wrap in the
Yes.
capture the gap.
So basically, what is happening internally, if you just want to understand it in a rough manner, it is this forward graph which you are making a CUDA graph out of. So ultimately, each FX graph has a mapping to a CUDA graph.
Yes.
And they try to disable CUDA graph for this FX graph thing, as in he like disable CUDA graphs for like CPU device and all.
Oh,
at
inside it.
ha if yes, it shall like do some analysis and all and switch off CUDA.
They do take the you can have one photograph or one FX graph, but you might also not have a photograph for a FX graph because there is security device inside.
Yes.
So the question also is that can you get a one photograph out of FX graph on fusing it?
Yeah, that is something that they have three of FX graphs, right?
They have tree of CUDA graphs.
FX graph, do you remember?
FX graph. FX graph trees, I have not heard of that.
Oh,
There is something known as CUDA graph trees.
I see.
As in what happens ki like the CUDA like ultimately this when everything is in full fledged, you do not need this forward graphs altogether. You shall be like in the fast path, you shall be executing CUDA graphs. So I don't know, like that is their decision choice. Huh. Huh.
Because each node is one node. Can you not that?
Yeah, like the thing is, there can be situations where we were saying ki like I say, FX graph might be breaking for some reason, but that reason is not necessary condition for like CUDA graphs to break or something like. Yes.
So if you pick it up, you won't see it.
Hmm.
But it will be an interesting thing to see. Right now, also the optimization one or two, whatever it is called, the one, I think it's doing is that not all effects graph mapping to CUDA graph because of simplification and so on. So he is actually trying to make more effects graph to CUDA graph, but that doesn't make multiple effects graph mapping to single CUDA graph. That's still not a problem.
Hmm.
Okay, fine.
Yeah, this is what I had.
Can you share this thing?
Yeah, I shall be posting it.
Put it on the
Put in. Yeah. Okay. Like you can just run this document as is, or it just you can read it there. I have also written whatever is. Yeah. Anybody has any question?
Yeah, you will.
Online, anybody has any question?
No, I'm
Then
good.
okay.
No, you are aware. Because when Neha is there, he's not asking question. I feel like Neha is sleeping.
No, I'm getting texts from Divya.
Okay, fine.
Okay.
But the one thing you should appreciate over here, this is a lot of internals, understanding, so on, without much documentation. It's difficult.
Yes.
You have built the knowledge base, which you should try to extract, and going to essentially. It is also. Because this gives you an advantage over others, and then think of it like those who are doing, you can just see the actual development of PyTorch. Of course, those people know inside out. They are not the researchers. You can see it clearly in Ask man, that is so poorly written. So, which means that you have the advantageous situation where you can actually leverage this. Good.
As in, what I was also saying, ki, like,
So that's probably saw that it's a substantial thing and but then give up.
So people already like impressed by the.